So, good evening, everyone. We will wait for 2 more minutes, then we will start for this problem solving session. So, good evening, everyone. Welcome to the week 7 of the NPTEL course. So, today we will, as usual, we will do, I will give you a brief introduction of what was taught in the week 7 modules, and then we will try to solve the previous year question of week 7. And then there will be 2 more questions based on the tutorial on fermentation and transistrification, and this will be all for today's problem solving session. So first, let's start with the module 1 of week 7. So fermentation has 2 parts. One of the part of fermentation was in week 7 modules, and this is the second module of fermentation. So we have discussed already what is fermentation and how energy is produced from fermentation. What is the production of ethanol from different feedstock, and what are the pre-processes required for lignocellulosic biomasses, and production of ethanol from starchy crops, then production of ethanol from lignocellulosic biomass, what are the pre-treatments, and what is detoxification and hydrolysis. So in this module, we will discuss about what are the microorganisms which are involved in fermentation, and what is the route for the ethanol production through gasification, and finally, butanol production from lignocellulosic biomass. So these are the reactions which shows the fermentation of glucose, xylose, cellubiose, or xylobiose to ethanol. So we can calculate the ethanol yield as C, that is the concentration of ethanol, into V, that is the initial volume of liquid medium, divided by mass of the mass of the substrate used. So we can calculate the ethanol yield using this formula, and then we can also calculate the ethanol productivity. So ethanol productivity is the amount of ethanol that is produced per unit substrate utilized per unit of time. So basically, what is ethanol productivity is ethanol yield. So ethanol productivity is ethanol yield per unit time. That is amount of ethanol produced per unit of substrate utilized per unit time. So it is typically determined when the ethanol concentration is maximum. So ethanol productivity is C, that is the concentration of ethanol, then V is the initial volume of liquid medium divided by M, mass of the substrate divided by time. So we can also calculate the maximum theoretical ethanol yield. It is calculated using the formula ethanol produced in reactor upon initial sugar in reactor into 0.511. It is a factor calculated for conversion of ethanol from sugar. Then the microorganisms used for fermentation of lignocellulosic biomass. So the sugar which is present is mainly hexose sugar, that is glucose. One of the hexose sugar is glucose. It has 6 carbon. So this is a figure of sugar, glucose, one of the sugar. So it has 6 carbons in its ring. So most of the sugar for starch-based ethanol production is mostly hexose sugar like glucose. And for lignocellulosic biomass mixture, we have pentose and hexose as sugar. So pentose has 5 carbons in their ring and hexose has 6 carbons. So the most traditional microorganism for fermenting sugar is yeast. This is the name of the yeast, Saccharomyces cerevisiae. It is one of the traditional fungi, that is yeast, used for fermentation. So, but one of the limitation of this is that the natural strain of this yeast can ferment only 6 carbon sugars, and it can hardly ferment pentose. So some of the new yeast strains such as Specia striptease and other can ferment xylose, but they cannot ferment hexose. So these yeast have limitation. They are suitable for a particular type of sugar. So the bacterial strains used for ethanol fermentation are Zymomenes mobilis and others, because they have the capacity to ferment hexose sugar very rapidly. So one of the options for fermentation of both pentose and hexose is use of the genetically modified bacteria and yeast. This is a genetic modification is a very current field and it's going extensively. So a lot of research is being done to produce strains capable of fermenting both pentose and hexose by a same type of strains. So next is the product recovery. So through fermentation, we will get ethanol, alcohol, we will get some wastewater, we will get some residue, but we need to purify purify to get almost 99.9% ethanol. So there are 2 routes. One is the thermal route, which was discussed in the previous module in week 6, that in thermal route, we do distillation and followed by some drying to get the product as ethanol. And there is one other route, which is a low temperature route, in which some membrane processing is used and molecular sieve water absorption is used to get ethanol. So we'll move forward. So some of the alternate routes for ethanol production from lignocellulosic biomass is, one is the fermentation route in which we get the ethanol. Then one of other routes is, first we do gasification and then we get syngas, and that syngas is used for thermal reaction with catalyst to produce the ethanol, or that syngas can be used for taking place the biological reaction to produce the ethanol. So the bacteria used for biological route for production of ethanol is this Clostridium jungdohali, and these microorganisms can ingest carbon dioxide, carbon monoxide, and hydrogen, and these can produce ethanol and water. So next is butanol production from lignocellulosic biomass. So butanol is one of the co-products of ABE, that is acetone, butanol, and ethanol fermentation. And the ratio of proportion of the acetone, butanol, and ethanol are in the ratio of 3:6:1. So these are some of the strains of the microorganisms which are capable of converting a broad range of carbon sources to fuels and chemicals. So the ABE fermentation, that is fermentation of acetone, butanol and ethanol, is biphasic. It involves two steps. First is the acidogenesis followed by solvitogenesis. So acidogenesis is a step which involves the production of acids. Some of the acids produced are acetic acid and butyric acid. And then the next step is solventogenesis. It is related to the production of the solvents, that is acetone, butanol or ethanol. One of the advantage of this process is that ABE producing bacteria can utilize both starchy as well as lignocellulosic substrates. There is no pre-treatment required for removal of lignin here. One more beneficial of this strain is that it can metabolize both pentose and hexose sugar in the biomass, present in the biomass. So, but there is one problem is that butanol is very toxic to the fermenting microorganisms. So, as soon the concentration of a butanol is greater than 2%, then it start inhibiting the growth of these fermenting microorganisms. So, some techniques are used for recovery of the butanol from the product. So there are various methods to recover butanol from the product. So the first step one is through adsorption. Here is a fermenter, and next is a adsorption column. The product is passed through this column, and then we get the butanol. Then it gets exhausted. After the column is exhausted, the new column is put in the place, and the exhausted column is regenerated, and we get the output from this column in the form of butanol. So next is the butanol recovery by pervaporation. It is basically a membrane-based technology, which consists of a non-porous or molecularly porous membrane. It means some of the molecules can pass through these membranes, but it inhibits other molecules to pass. So what happens? From these membranes, the butanol pass and get pass through these membranes, and we get the butanol from the membranes, and whatever is retented on these membrane is we get as retentate. So next is by using supercritical fluids. So supercritical fluids have both liquid-like and gas-like properties, and these can dissolve organic materials very efficiently. So the feed in which butanol is present is the feed on one of the columns filled with supercritical fluid. These fluid absorb the these fluid dissolve the butanol, and we then separate the butanol from the product, and we get the butanol. So next is by gas stripping. So here the product is fed in one of the condensers, and because of the condensation we get the product and butanol in the product. Next is by liquid extraction. So the acetone, butanol and ethanol are separated by extracting solvent, and then these solvent extract the acetone, butanol and ethanol, and then finally these columns get exhausted and they are regenerated and reused. So next is butanol recovery by distillation. It is one of the traditional methods for recovery of butanol from aqueous fermentation broth. But the high energy is required for boiling the solution, because butanol has higher boiling point than water. So lot of energy is required for making this for boiling the solution. So, and finally, we get the butanol and condense the distillate. After distillation, we get the butanol. So, what some of the advantages and disadvantages of butanol recovery technologies are: first is absorption. It is very easy to operate. The energy demand is very less, but it has low selectivity and high material cost. And there are the lot of cost is associated with the regeneration of the adsorbents. So here the energy requirement is in the range of 1.3 to 33 megajoule per kg. Next process is the distillation. It is one traditionally used process for methanol recovery. Less infrastructure is required, but operational cost is very high due to low concentration of butanol, and it is very high energy intensive because we have to boil the product to get the butanol. Next is gas stripping. The advantage is it is very high efficient, but the problem with it is it has low selectivity, and also the energy requirement is high. It is 14 to 31 megajoules per kg. Next is liquid extraction. It has low energy requirement, but it has high operational cost, and the energy requirement here is in the range of 7.7 to 26 megajoule per kg. Next is pervaporation. It involves the removal of selective solvents. It is a less energy intensive process, but there is lot of cost associated with the membranes used, and these membranes are vulnerable to temperature and other compounds or contaminants present. So the energy requirement here is in the range of 2 to 145 megajoule per kg. And next is a supercritical fluid extraction. It is cost effective and recyclable, but it is a very recent technology, and lots of research is required for optimization of this process. So next is some of the microbial strains which are used for butanol production. These are the feedstock, like for wood, aspen wood, Clostridium acetobutylicum P262 strain is required. So these are some of the bacterial strains which are used for butanol production from different biomasses. So we'll move to module 4, because module 2 and 3 was tutorial on fermentation and biomass production. So we will move to next module, that is Transistrification. So these are the contents for Transistrification. So what is our Transistrification? In this process, what happens is some alcohol react with some oil, that is triglyceride oil present in plant oils, to form fatty acid alkyl esters. This fatty acid alkyl ester is the biodiesel, and along with this, glycerin is produced. So some heat and catalysts such as the sodium hydroxide and potassium hydroxide are required for this reactions to take place. So this is the plant oil which reacts with methanol, and some catalyst, either KOH or NOH, is used to produce the biodiesel. Along with the byproduct is the glycerol or glycerine. So different organic waste require different pre-treatment for production of bio oil. So if we have waste oil seeds, so first oil extraction is done from the seeds, and then we get bio oil, and this bio oil is transistrified to produce the biodiesel. Next, if we have some waste oil or cooking oil, then it is directly transistrified to produce the biodiesel, or if we have grease, then grease also goes through transistrification process to produce the biodiesel. So next is the how we extract bio oil from seeds. So there are two methods for extraction of bio oil from seeds. First is the conventional method, and next is the advanced method. In conventional method, we have two methods. First is the expeller press method, and next is the solvent extraction method. So in expeller press method, seeds are pressed or crushed into smaller particles, and in solvent extraction method, Seeds are dissolved after crushing, they are dissolved in some solvent to extract the oil from it. So this is one instrument showing for oil press, and this is for solvent extraction. Next, what the factors affecting the oil extraction is what type of solvent we are using. So if we have non-polar solvent, if the oil is non-polar, then we should use non-polar solvent for maximum miscibility them between them. And if we have polar bio oil, then polar solvent is used. So next factor which affect the bio oil extraction is biomass to solvent ratio. Next is the temperature. It should be optimum. Then what is the method used for extraction of the oil? Then what is the extraction time, moisture content, and particle size and shape? So here is the comparison of various lipid extraction processes. First is the oil press. It is simple to use. No solvent is required, but large biomass is required, and also it is a very slow process for extraction of bio oil. Next is solvent extraction. So the cost of solvent is very high, but the solvent can be recovered after use. So the problem with this technology is that it is expensive, as well as the solvent which is being used, it may be toxic or flammable. Next is these are supercritical fluid extraction and ultrasonic assisted extraction are the advanced method for extraction of bio oil from oil seeds. So in supercritical fluid extraction, the solvent which is used is non-toxic and non-flammable. But the problem with is there is a limited interaction between the supercritical CO2 and biomass. Next is ultrasonic assisted extraction. For the advantage with this process is that less extraction time is required and less solvent is required. But the scale up of this technology at a commercial level is not very easy, and also it requires lots of power to operate. Next is some of the common fatty acids which are present in the bio oil along with their elemental formula, structure, and what are the melting point. So next is why upgradation of bio oil is required to biodiesel. Why we are not using the plant oil as it is. So the reason is that the plant oil is much more viscous than the conventional diesel fuel. So it is around 11 to 17 times more thickened than the diesel fuel we used. So also the plant oil has very different chemical properties and combustion characteristics as compared to the conventional diesel fuel. So if the fuel will be too thick, then the combustion will not be proper, and the performance of using this thick oil as diesel will not be very good. So that's why the cooking oil or bio oil are first recycled and then they are upgraded to produce the biodiesel. So the waste oil, the cooking oil, and recycled grease lose their properties and requires recycling and reuse. Again, transistrification is one of the process which improves the quality of these feedstock and impart fuel properties that it makes suitable for using this oil as diesel. So bio oil is basically mixture of fatty acid alkyl esters. It is non-hazardous, non-toxic, and biodegradable, and it reduces air pollutants such as the particulate matter, carbon monoxide, hydrocarbons, air toxins. These are produced by combustion of the diesel, conventional diesel, which are used in engines. So some of the bio oils burn more efficiently than even the petroleum diesel, and it has high lubricity and can reduce the engine wear. And since the wear of engine is reduced, so the engine can be used for longer time. So it can also be used, basically biodiesel are mixed with conventional diesel and then they are used, but it can also be used for vehicles in pure form. But generally they are used in blend form. So the most common is B20. B20 means 20% biodiesel and 80% diesel. So if we are using blend of biodiesel along with the conventional diesel, so there will no requirement of engine modification. We can use this blend in the already present engines of the vehicles. So one of the problem is the high viscosity and flash point, which needs upgradation for biodiesel. So we'll see what is viscosity and flash point in the next slides. So what are the important properties which are required for biodiesel? First is the ash. Ash, after combustion, some amount of unburnt carbons and other things will be present. And basically, ash is the measure of amount of metals that is contained in the fuel, because all other carbon and other compounds will be burned, and those that can't be burned will be present in the ash. Next is density. Density is, in simple words, is weight per unit volume. So biooils are denser than biodiesels. And for example, gasoline and diesel fuel gives comparable engine by weight, but diesel is dense and hence gives more energy per liter. Because of high density, diesel gives more energy as compared to gasoline. Next is cloud point. There is a temperature at which the oil starts to solidify, and this point is known as cloud point. So if we are using the vehicle or engine at temperature below the cloud point of the oil, then some heating will be required, so that solidification of bio-oil can be ignored. Next is pour point. This is the temperature at which the oil in solid form starts to melt or pour. So in cases where the temperature fall below the melt point, the entire fuel system, including the fuel lines and fuel tanks, will need to be heated. So next is CTA number. It is one of the very important properties for use of any fuel for combustion. Next, because the higher the cetane number of the fuel, the shorter the delay interval and greater is its combustibility. So if some fuel has high cetane number, then there will be very less delay between the beginning of injection and auto ignition of fuel, and it will give greater combustibility. So if this is CT number of a compound which is 100, for methyl naphthalene it is 0, and for isocetene it is 15. So most the fuel which will have highest cetane number will have higher combustibility. So this fuel will have the highest combustibility. So we can also calculate cetane number by burning the fuel in cooperative fuel research engine. In this engine, the fuel is burned under standard conditions, and then we get the cetane number using this procedure. And then we calculate the cetane number by determining the mixture of cetane, that is hexadecane, and isocetane. What is the proportion of these in the mixture, and then we calculate the cetane number from this. Next important point, flash point of a fuel is the minimum temperature at which the fuel will ignite on application of an ignition source. So flash point varies inversely with the fuel's volatility. If fuel will be more volatile, then flash point will be lower, and if fuel will be less volatile, then flash point will be more. So minimum flash point temperatures are required for proper safety and handling of fuel so that ignition does not take place. So the two methods, two types of flash point measurements are open cup and closed cup. So next is the heating value. So heating value is the amount of heating energy released by combustion of a unit value of fuel. So if you are burning 1 kg of fuel, then the amount of energy released by the combustion of that fuel will give the heating value. Next is the iodine value. So it is the amount of iodine which is absorbed by 100 ml of the given oil. Next is potassium percentage. So how much potassium is present in the fuel? Next is sulfur percentage. What is the percentage of sulfur in the fuel? Next is viscosity. So viscosity refers to the thickness of the oil, and it is measured by measuring the time taken for a given amount of oil to pass through an orifice of a specified size. So when liquid flows through the tubes, then this equation is used to find the viscosity. So we can also find the viscosity using viscometers. So viscometers can, the different types of viscometers are Oswald viscometer, falling sphere viscometer, falling piston viscometer, oscillating piston viscometer, vibrational viscometers, rotational viscometers, and bubble viscometer. These are some of the viscometers which can be used to measure the viscosity of the oil. So next is the comparison of properties of biodiesel from different vegetable oils. So different oil like diesel, soybean oil, biodiesel from soybean oil. What is the Babusi oil? Next is biodiesel from Babusi oil. So these are the different oil, diesels and oil, and these are compared on the basis of kinematic viscosity, CTA number, heating value, cloud point, and other properties. So next is the generalized flow for biodiesel production from various feedstock. So if we have a Transistrification reactor, then recycled grease is first pre-treated by dilute acid esterification, and then it is fed into the Transistrification reactor, and then separation takes place. And then finally we get the glycerin and we get the biodiesel, and some refining of biodiesel and glycerin takes place, and we finally get the product as and we also recover the catalyst on the methanol which were used in the esterification, and we get the product as well as the methanol and catalyst used in the Transistrification process. So the complete process for production of methyl ester or bio-oil from plant oil and other feedstock involve 5 steps. First is the acid esterification. Next is Transistrification, then methanol recovery, then biodiesel refining, and glycerin refining. So we will discuss these in the module 5 of week 7. So the steps used for upgradation are: first is acid esterification. So the free fatty acids in biodiesel, these can react with the alkali catalysts which are used are NOH and KOH, and these can produce soaps. So what happens? The free fatty acids react with the catalyst and form the sodium or potassium salt of fatty acids, and these are called soaps, and these can degrade the quality of the biodiesel produced. So if the feedstock has a low level of free fatty acids, that is less than 4%, then these can be managed by using additional catalyst and allowing the soap to form. And if the feedstock has free fatty acids greater than 4%, then the feedstock are first filtered and they are pre-processed to remove the water and other contaminants like unwanted solids. Then the pre-treatment oil is fed to the acid esterification process, and then it is sent for Transistrification. Next is the alternative methods which can be used to remove or manage free fatty acids are enzymatic method, but it is very costly and it is not very popular. And next is the glycerolysis, in which glycerol is added, and these reacts with free fatty acids in presence of zinc chloride as a catalyst and convert the free fatty acids to monoglyceride and diglyceride along with water. Sorry. So next process used is we can calculate how much conversion of free fatty acids has taken place by using this formula, where S naught is the initial acid value, SI is the acid value at some reaction time divided by S naught. So these are the formula. Then next is transesterification. So the plant oil which contains less than 4% of free fatty acid is first filtered and then pre-processed to remove water and other contaminants. And then these pre-processed oil is fed to the transesterification process along with any products of the acid esterification process. So the catalyst used here is KOH. It is dissolved in methanol and then mixed with the pre-treated oil. And some heterogeneous catalyst can also be used in place of KOH. So if acid esterification process is used, then additional alkali catalyst must be used to neutralize the any excess acid which may be remaining in the oil after acid esterification. So once the transesterification process is complete, the major co-products is biodiesel and glycerin, and these are separated in two layers because of difference in their density. Next is the factors which affect the transesterification process performance is the reaction temperature. What is the temperature used? What is the reaction time used? What is all alcohol to oil mole ratio? What is the catalyst concentration? Free fatty acid content? What is the mixing being used? Water content? What are the types of alcohol and catalyst type being used? So it is here is a chart which shows some of the heterogeneous catalysts which are being used for biodiesel production. So for example, for sunflower oil, the solvent used is methanol and the catalyst uses strontium oxide. And these are the operating condition, that is temperature is 65 degrees centigrade, oil to ratio is 12:1. Catalyst loading weight percentage is 3, reaction time is 0.5 hour, and the yield of this is 90%. Next is after acid esterification and transesterification, we have methanol recovery. So the methanol is used as solvent. So methanol is usually removed immediately after the biodiesel and glycerin have been separated. And this is done to prevent the reaction from reversing itself. So recovered methanol is cleaned and these are recycled back to the beginning of the process for use in the next batch. Next is the biodiesel refining. So once the glycerin has been separated from the product, the biodiesel goes through series of cleaning or purification of or upgradation of steps to remove the contaminants or like alcohol or any residual catalysts and soaps if are present, then they are removed. Next is glycerin refining. So the crude glycerin which we have obtained from the transesterification process, these may be recovered or may be used in a fuel blend for steam production. So the crude glycerin basically contains unreacted catalyst and soaps that must be neutralized with an acid, and the water and alcohol are also removed from the glycerin to produce 50 to 80% of the crude glycerin. And the remaining contaminants which are present in the glycerin are the unreacted fats and oils which need to be removed. So if there is a large biodiesel plant, then glycerin is further purified through a series of steps to produce 99% or higher purity glycerin. So here is a chart which shows if we have waste cooking oil, some screening is done, then clean waste oil is fed to the feed tank. Then it is methanol is added, then esterification is done, and then after esterification, these are the products which we get and the modifications which we use to get the end product. So these are the slides for pre-treatment of mixed waste oil. So please go through these slides. We'll move to the previous year questions. Sorry, I forgot to give my introduction in the beginning. So my name is Asma Parveen. I'm one of PhD scholar in Civil Engineering Department at IIT Kanpur, and this course is being instructed by Professor P. Mandal from Department of Chemical Engineering, IIT Roorkee. So we will see the previous year questions for this week. So I'll give you 2 to 3 minutes for the theoretical questions, and I will give you 5 minutes or more based on the for the numerical questions. So the first question is, the maximum theoretical ethanol yield is given by. We have to find out which formula is used to calculate the maximum theoretical ethanol yield. So I'll request you all to please try to solve these questions and just write whatever option A, B, C, D you think is correct in the chat box. And I will give you 2 minutes for this question. So just take your time and write your answer. So the correct answer is B. The maximum theoretical ethanol yield is given as the ratio of ethanol produced in reactor to the initial sugar in reactor into 0.511 into 100. So next question is, water above its critical temperature and critical pressure is called supercritical water. The critical temperature and pressure of water are, so I'll give you 2 minutes. Just write your answers in the chat box. So the correct answer is C, the critical temperature is 374 degrees centigrade and pressure is 2.2 bars. So next question is, which of the following is not a type of viscometer? Postwald viscometer, bubble viscometer, Newton viscometer, or rotational viscometer? So I will give you 2 minutes. Just write your answers in the chat box. So I got 5 answers and they say the correct answer is C. So obviously the correct answer is C. Newton viscometer is not a type of viscometer. So next question is, in the following flow sheet of biodiesel production from mixed waste plant oil, identify A and B. So here is a flow sheet for the production of biodiesel from the mixed plant oil. We have to identify what is A and what is B in this figure. So A can be a crude biodiesel tank, or B can be esterification reactor, or A is esterification reactor, B is crude biodiesel tank, A is methanol recovery tank, or B is crude biodiesel tank, or A is esterification reactor, or B is methanol recovery tank. So we have to identify what is A and B. So again, I will give you 2 minutes. Just write your answers in the chat box. So I got only 3 answers. I encourage everyone to write your answers and then we will move forward. So I'll give you 2 more minutes. So please write your answers in the chat box for question number 4. So the correct answer is B, where A is the esterification reactor and B is the crude biodiesel tank. So next question is, the correct sequence of operations involved in butanol recovery by adsorption is. So we have the figure, we have to identify what is the current sequence and what is A, B, and C. Whether A is adsorption column followed by fermenter and then regeneration column, or fermenter, adsorption column, and then regeneration column, or then A is fermenter, B is regeneration column, and C is adsorption column, or A is adsorption column, B is regeneration column, and C is fermenter. So I'll give you 2 minutes. Just write, everyone please write your answers in the chat box and then we'll move forward. got six, so I got six answers. So let's see what is the correct answer. So A is the answer. Correct answer is B, where A is the fermenter, B is the adsorption column, followed by C, the regeneration column. So we'll move to the question number 6. It is a numerical based question. So the question is, in a high rate biogas plant, food waste is anaerobically digested to produce biogas. The slurry contains 10% of solid food grains. The elemental composition of the food grains on dry basis is carbon is 60%, hydrogen is 7%, oxygen is 25%, nitrogen is 5%, and these percentages on the basis of mass. The next is around 80% of the food grains are converted to biogas and all the converted hydrogen form methane. If the flow rate of the slurry is 5,000 liters per day, calculate the rate of biogas production. So it is a bit lengthy question. So I'll give you 5 minutes. Just solve the question and write whatever option you are getting. Please write that in the chat box. So I got 3 answers. So I'll give you 2 more minutes. So I'll give you 2 more minutes to solve this question. So I'll encourage everyone to please try to solve this question, and then we'll move forward. So the correct answer is B. We'll see how to solve this question. So we have given the solid percentage in slurry. So the flow rate, first we'll see the flow rate of the slurry is 5,000 liters per day. And 10% of this is 10% of the slurry is solid. So the amount of dry solid food grains used is 5,000 into 10%, 0.1 is 500 kg. So we'll assume the density of slurry to be 1 kg per liter. And we have been given the percentage of the different elements, and we will find out of this 500 kg, what is the amount of carbon. So the carbon percentage is 60%. So out of 500, 300 kg will be the carbon. The hydrogen percentage is 7%. So hydrogen present in 500 kg dry food grains will be 500 into 0.07, that is 35 kg. Similarly, we will find out the amount of oxygen in the dry food grains, that will be 5.25. 125 kg, and nitrogen is 8%. So 500 into 8% will give us the amount of nitrogen present in 500 kg dry food grains. So next, in question it is being given that around 80% of the food grains are converted to biogas. So since the 80% of food grains are converted to biogas, and biogas is a mixture of CO2 and methane. So we will find out how much amount of carbon and how much amount of hydrogen has converted to biogas. So we have 300 kg of carbon and 35 kg of hydrogen. So out of this, 80% of the carbon has converted to biogas. So the carbon amount of carbon converted to biogas will be 300 into 0.8. That will be 240 kg. And the hydrogen converted to biogas is 35 kg of hydrogen into 80%, that is 28 kg. Next, in the question, it is given that 80% of the food grains are converted to biogas, and all the converted hydrogen form methane. So this as converted to biogas is used for methane production. So since all hydrogen is converted to methane, So the methane production will be 16 by 40. 16 is the molar mass of methane and 4 is the mass of hydrogen into 28 kg. So 4 grams of hydrogen is present in 16. We can find it by unitary method. That is 4 grams of hydrogen are present in 16 gram of methane, or 4 grams of hydrogen produces 16 gram of methane. So 28 kg of hydrogen will be 16 by 4 into 28, that is 112 kg of methane. So we'll convert into moles, 112 divided by molar mass of methane, and we will get 7 kilomoles because our mass here is in kg. We will divide by molar mass in grams, and we will get the overall unit in kilomoles, or 7,000 moles. Next is we will find out how much amount of carbon is used for methane production. So the carbon used for methane production will be 12 by 16. 12 is the molar mass of carbon. Out of the 16 grams of methane, we have 12 grams of carbon in that. So 12 by 16 into the amount of methane that is produced. So 112 kg of methane is produced. So the amount of carbon used for methane production is total methane into the amount of carbon per mole of methane. 12 by 16 will be 84 kg. And next we will calculate how much carbon is converted to CO2, or what is the amount of carbon used for CO2 production. So we have total 240 kg of carbon in the biogas. Out of this 240 kg, we have 84 kg of methane. Sorry, we have 84 kg of carbon in the methane. So the remaining carbon will be converted to CO2. So the carbon used for CO2 production will be 240 minus 84, that is 156 kg. So the CO2 produced will again be 156 into 44 by 12. 44 is the molar mass of CO2 and 12 is the molar mass of carbon. And we will get 572 kg of CO2. And after converting to moles, we will divide it by the molar mass of CO2 and we will get 13 kilomole. So we have 112 kg of methane and we have 572 kg of CO2. So overall overall biogas produced is 684 kg. And we can also, So the correct answer is 684, that is B. So I hope you got the idea how to solve this question. And someone was asking me that, Pramod was telling that in question 1, A and B both are correct. So we'll see what is question 1. No, Pramod ji, can you please unmute yourself?
Yeah, ma'am. I think
So I'll see, E and B both are different formula, and the formula B is correct for calculating the maximum theoretical ethanol yield. It is the ratio of ethanol produced in the reactor
number
to
question.
the
Second number
sugar
question.
in reactor into 0.051.
Second number question, ma'am.
Sorry, 0.511.
Yeah,
So one is fine. Correct answer is B.
actually, I'm talking about the second number question. Critical water temperature.
Next, we'll move to next question. So next question is also a numerical. So the question says a food waste is digested through thermochemical as well as biological routes. In the first case, the energy requirement is 28% higher than the second case. That is, the energy requirement in thermochemical process is 28% higher than the biochemical routes. Whereas the sugar production per unit mass of food waste is 22% more in first case than that of second case. The pre-treatment energy efficiency for thermochemical routes is dash percentage of that of biological route. So we have to find out the what is the pre-treatment energy efficiency for thermochemical routes in terms of biological routes. So I will give you 5 minutes. Just solve this question and write the answer in the chat box. So I got three answers as C, 95.3%. Let's see. So as we know, the pre-treatment energy efficiency is given as ratio of total soluble sugar yield to total energy consumption during pre-treatment. So we will assume a basis that we will assume the mass of food waste as 100 kg, and biochemical routes uses X megajoule of power and produces Y kg of sugar from this 100 kg waste. Now we will see from from question it is given that thermochemical routes require 28% higher energy. So thermochemical route will use X into 1.28 megajoule of power and it produces 22% more sugar. So the sugar production through thermochemical route will be 1.22 times of that produced by biochemical, that is 1.22 into Y kg of sugar from 100 grams of waste. So we have to find the percentage of pre-treatment energy efficiency for thermochemical routes as percentage of biochemical routes. So pre-treatment energy efficiency for biochemical route will be Y by X. That is, Y is the amount of sugar produced to the total energy consumed. So Y is the amount of sugar produced and X is the megajoule of energy consumed. And for the thermochemical routes, the pre-treatment energy efficiency will be 1.22 times Y upon 1.28 X, and it will give the ratio as 0.953 into Y by X. And Y by X is the pre-treatment energy efficiency for biochemical route. So the pre-treatment energy efficiency for thermochemical route will be 0.953 into 100, that is 95.3% of that of the biochemical route. So the correct answer is C. So we'll move forward, and the next question is, which of the following butanol recovery technology has disadvantage of high membrane cost? A adsorption, B distillation, C supercritical fluid extraction, or D pervaporation. So I'll give you 2 minutes. Just take your time and write your answer in the chat box. So I got three answers. So correct answer is P, pervaporation. In this membrane is used for extraction of butanol. So the correct answer is T. So we'll move to next question. Dash reaction converts plant oil to biodiesel. We have to find out what process is used or what reaction it is used to convert plant oil to biodiesel. A. Transistrification, B. Saponification, C. Fermentation, or D. Hydrolysis. So I'll give you 2 minutes. So I request everyone to please participate and write your answers. I'm only getting 2 to 3 answers for each question. So I request everyone to please write your answers in the chat box. So we'll see which is the correct answer. So the correct answer is A. Transistrification is used for conversion of bio-oil to biodiesel. Next, the last question is, the acid value can be calculated as, S is the acid value, C is the concentration of the KOH used for. So, sorry. We have to find out which of these formula are used for calculation of acid value, where S is the acid value, C is the concentration of KOH used for titration, V is the volume of KOH employed for titration, and M is the mass of the sample taken. So I'll give you 2 minutes. Just write your answers in the chat box and we'll move forward. So the correct answer is A. S is equal to 56.1 Bc by M. This formula is used to find the acid value. So now we'll solve one numerical on how to find the cross section of the digesters and how to find the dimension of the digester. So this is a anaerobic digester where the cross section of the digester is VD is the active digestion volume, VGST is the gas storage volume, VCOL is the gas collection volume, and VSL is the sludge layer volume. And the total volume of the reactor will be the summation of these volumes. And this is the difference between cross section and dimension. The dimension includes the values of the these geometrical parts of the reactor, that is the cylindrical part and top cover and the bottom cover. What is the volume of the top and what is the volume of the bottom cover? What is the volume of the cylindrical part? What will be the height of top and bottom round covers? What will the height of cylindrical portion? And what will be the radius? These are the dimensions of the reactor, and these are the cross sections of the reactor. So there is one more thing, H1, where H1 is the height between this cross section height where the active digestion volume ends, and the volume for gas storage starts, and there is a junction where the cylindrical portion ends, and these top cover starts. So this height is denoted as H1. So V1 is the volume of top head, V2 is the volume of bottom head, S1 is the surface area of top head, and V2 is the surface area of volume head. And these V3 is the volume of cylindrical part, R1 is the characteristic diameter of top head, R2 is the characteristic diameter of bottom head, H is the height of cylindrical portion, and H1 is the height of top head, H2 is the height of bottom head, R is the radius of cylindrical part, and D is the diameter of cylindrical part. And all these parameters, these can be related to D, that is the dia of the cylindrical part. So we will see how these are related. So these are the geometrical dimensions, and these are there are some formula to calculate what is the volume, dia, radius or height. And these are related with capital D, that is dia. And for reactor dimensions, sorry, for reactor cross section, that we can find the volume of each section by using these formula. So we have one numerical. So basically this numerical is the part of week 6. There was one numerical in the assignment in which we have to find out the volume of the digester chamber. So we will try to find out the dimension of this chamber. So in that question, the volume of the digestion chamber was 12.65 meter cube. So the question says the volume of digestion chamber required for the biogas production from cow dung of 12 cows having body weight of 80 kg each is 12.65 meter cube. Assume the temperature is 30 degrees centigrade, the solid content of cow dung is 15% and hydraulic retention time is 45 days. And one cow produces 10 kg cow dung daily. So question is, we have to find the dimensions of the reactor, and the first part of this question is we have to find the volume of cylindrical portion and height of the cylindrical section. So basically this statement is used to find the volume of the digestion chamber. I have already given you the volume, that is 12.65 question. So now we have to find the volume of cylindrical portion and height of cylindrical portion. For this, we first need to find out what will be the dia of the cylindrical section. And we can get the dia using this formula, that is dia is 1.3078 V to the power of 1 by 3. So I'll give you 5 minutes to find the dia and find the volume of cylindrical portion and height of the cylindrical portion. So just solve the question and write whatever value you are getting for dia as well as for volume of cylindrical portion and height for this section. So I'll give you 5 minutes. Please try to solve the question and write your answers in the chat box. I'm sorry, I was having some problem in sharing the screen, so I have reshared the screen. So please try to solve this question and we'll then move forward. So I haven't got any answer. So we'll see how to approach this question. So we have the overall volume, that is V of the digester, that is 12.65 meter cubes. And as we know, the diameter of cylindrical part is related with the volume as D as 1.3078 into V to the power of 1 by 3. We have V as 12.65 meter cubes. So we will put V in this equation and we will get the dia of cylindrical part as 3.047 meter. Now we have to find the volume of the cylindrical portion. So the volume of cylindrical portion will be pi d square h by 4. We need d, but we don't know what is the height of the cylindrical part. So what we will do is we will find this as so. So we have V3, the volume of cylindrical part as 0.3142 dq. So we will find the volume of cylindrical part as 0.3142 dq. We know what is d. We will put this in this equation and we will get the volume as 8.8884 meter cube. Now we know the volume of the cylindrical part and we will find the height using this formula, that is volume of cylinder is pi d square h by 4. We know d. We will solve and we will get the value of h as almost 1.22 meters. So I hope this is clear. If anyone have any doubt, then you can ask me, or otherwise we'll move to next part.
Madam, actually the digester volume is only the cylindrical portion, right, madam?
So
Hello?
I think everyone is no one has any doubt. So we'll move to next part of actually this question. So now we have to find the dimension H1, H2, R1, R2, V1, and V2. And already I have given you the slide for the formula. So we will use these formula now R1, R2. So I'm keeping this slide, I'm sharing this slide because we know the dia D is 3.047 and we have to find R1, R2, H1, H2. I think maybe you all don't remember the formula. That's why I'm sharing the slides to give you the formula. So just find out what is H1, H2 and R1 and R2 and please write your answers in the chat box. I'll give you 3 minutes to solve this question. Then we will see how to approach this question if you are not able to solve it. So we'll see what is the answer. So H1 is given as T by 5. So H1 will be 0.6094 and H2 is given as T by 8. T is 3.047 and we'll get H2 is 0.3809. R1 is 0.275 T times 0.725 times of dia of cylindrical portion, and it will come out to be 2.2091. And R1 is 1.0625 into D, that will be 3.2374 meters. And so I forgot to ask you for V1 and V2. So I'll give you 1 more minute to find out the volume of top head and volume of the bottom head. So we'll see what is the value for V1 and V2. V1 is given as 0.0827 into D cube. So we'll put the value of T here, 3.047, and we will get the volume of top head as 2.3395 meter cube. And V2 is given as 0.05011 D cube, and we are getting the V2 as 1.4176. So we have one more part. We have to find the gas collection volume and gas storage volume. So I will give you the formula. So these are the formula. We have to find the gas collection volume and gas storage volume. So I'll give you 2 minutes for these. Please solve and write your answers in the chat box. So I got one answer, but two volumes have been asked. So we'll see how to solve this question. So we have to find the gas collection volume and gas storage volume. So gas collection volume is given as 0.05 times of the total volume, and we have the volume of the digester as 12.65. So gas collection volume will be 0.05 times 12.65, that will be 0.6325. And the gas storage volume is given as 0.5 into VGST plus VD plus VSL into K. So this total can be given as total volume in minus the gas collection volume, minus the gas collection volume. We have gas collection volume is 0.6325 and total volume is 12.65, and K, we assume K to be 0.4, and then we put these values and we get the gas storage volume is 2.4035. So I got one answer as 2.516, but none of these answers are 2.516. So we will see what will the volume of gas storage volume, because we have we can find the gas storage volume by using two formulas, either by this, or we can find the gas storage volume by using gas storage volume is given as 50% of the daily gas yield. So here it is given 50% of the daily gas yield. The total solids is 120 into gas production rate per kg total solids per day, that will be 0.15. These are the these are the values we are using. 0.5 into total solids into M is the gas production rate per kg of total solids per day, and this is taken as 0.28 and K is taken as 0.4. So we are using these values. So we have 0.5 into gas production rate, that will be 0.28, and we have to find the total solids. So we will find the total solids from the question. We have been given 12 cows are given, and each cow is producing 10 kg cow dung, and out of this 15% is the total solid content. So we will find the total solid content using these formula, using this, and we will get the total solids as 120. We will get these as 120 into 0.15, because 15% is the total solids, and 12 cows are producing 10 kg of cow dung, that will be 120 into 15%, 0.15. So TS will be 120.15. Gas production rate is 0.28, and then 0.5 times of this, we will get the gas storage volume as 2.52 meter cubes. So we are getting two values for gas storage volume, and for being in safer side, we will take the larger of these values. So the gas collection gas storage volume will be 2.52 meter cube, and the gas collection volume will be 0.6325 meter cube. So now these are the questions which we were supposed to solve today. So thank you so much for joining, and if anyone has any doubt, then you can ask me, or if you all have no doubts, then you can leave the meeting, and we will meet next week on the same day. Maybe there will be some different timing, because on next Sunday written exam is scheduled. So maybe this session will be on Saturday or Friday or any other day before Sunday. So you will get a mail regarding that. So thank you so much for joining. Have a good day. So if you have any doubt, you can ask, or so.
No, ma'am. Thank you.
I think no one has any doubts. So thank you so much for joining. Have a good day.
Thank you.